Twice a day, every day, the entire ocean rises and falls, pulled by an invisible hand stretching across 250,000 miles of empty space. This has been happening since before there were shores to wash against, since before there were creatures to watch the water climb. Tonight, as you settle into stillness, let us follow that invisible hand. Let us trace the ancient conversation between the moon, the sun, and the restless sea. A conversation written in salt and gravity, older than memory itself. Welcome to Let's Learn While You Sleep. Tonight we rest beside the ocean, where the water is doing what it has always done, breathing in, breathing out, rising and falling to a rhythm set not by wind, not by weather, but by the quiet pull of worlds beyond our own. There is something deeply comforting in the tides. They are among the most reliable phenomena on Earth, as predictable as sunrise, as patient as stone. Fishermen have planned their lives around them. Ancient civilizations built calendars to track them. And yet, for most of human history, no one could explain why the sea climbed the shore and then retreated twice each day, without fail. Tonight, we will unravel that mystery together, gently, slowly, with no hurry at all. We will learn how the moon's gravity reaches across roughly 239,000 miles of vacuum to lift billions of tons of seawater. We will discover the quiet role of the sun and the strange truth that the tide pulls the earth itself, not just its oceans. Let your breathing slow, let your thoughts soften, and let the tide carry you towards sleep. To understand the tides, we must first understand gravity, not as a force that merely pulls things downward, but as a force that reaches across the emptiness between worlds. Every object that has mass exerts a gravitational pull on every other object that has mass, no matter how far away. This is one of the great insights of Isaac Newton, who, in his Principia Mathematica published in 1687, described gravity as a universal force, universal meaning that it applies everywhere to everything without exception. The moon, our closest celestial neighbor, orbits the Earth at an average distance of approximately 239,000 miles. It is a modest world, roughly 1/80th the mass of the Earth, and yet its gravitational influence on our planet is profound. Because gravity weakens with distance, following what physicists call an inverse square law, the side of the Earth facing the moon feels a slightly stronger pull than the center of the Earth, and the center feels a slightly stronger pull than the far side. This difference in gravitational force across the body of the Earth is called a tidal force. And it is this difference, this gentle gradient, that lifts the ocean. Imagine, if you will, the Earth surrounded by its thin shell of water. The moon's gravity pulls the water on the near side slightly toward itself, creating a bulge, a subtle swelling of the sea. But something perhaps more surprising happens on the opposite side of the Earth as well. Because the far side experiences less gravitational pull from the moon than the Earth's center does, the water there is, in a sense, left behind. It lags and forms a second bulge pointing away from the moon. So at any given moment, there are two great swells of ocean water on the Earth, one facing the moon and one facing away. As the Earth rotates beneath these bulges, completing one full turn roughly every 24 hours, most coastlines pass through both swells. This is why the majority of places on Earth experience two high tides and two low tides each day. The ocean is not sloshing back and forth. Rather, the Earth is spinning inside a shape that the moon's gravity has gently molded. An elongated envelope of water held in place by the quiet arithmetic of distance and mass. Now, you might wonder, if the moon alone were responsible, the tides would follow a perfectly simple pattern, and we could leave our explanation there. But the ocean's rhythm has another partner, one far more distant but enormously more massive: the sun. Our star sits roughly 93 million miles away, and its mass is about 27 million times greater than the moon's. And yet, despite that staggering difference in mass, the sun's tidal influence on Earth is only about 46% as strong as the moon's. This seems paradoxical at first, but it reveals something beautiful about tidal forces. They depend not just on the mass of the pulling body, but on how rapidly its gravitational pull changes across the width of the Earth. Because the sun is so far away, its gravity is nearly uniform across the Earth. The near side and the far side feel almost the same pull. The moon, being so much closer, creates a much steeper gradient, and it is the gradient, not the absolute strength, that raises the tide. Still, the sun's contribution is far from trivial. Roughly twice each month, when the Earth, moon and sun align during a new moon or a full moon, their tidal forces combine, pulling in the same direction. These are called spring tides, and the name has nothing to do with the season. It comes from an old English and Germanic word meaning to leap or to surge. During spring tides, high tides are higher than average, and low tides are lower because the sun and moon are working together. About a week later, when the moon is in its first or third quarter, meaning it sits at roughly a right angle to the sun as seen from Earth, their tidal forces partially cancel each other. The sun's pull diminishes the moon's bulge, and the result is neap tides, gentler, more subdued, with a smaller difference between high and low water. The word neap may come from an old English term meaning scarcely or barely, a fitting name for tides that seem to hold their breath. And so the ocean moves through a fortnightly cycle, swelling and softening, surging and resting, as the moon wheels through its phases, a pulse as steady and ancient as any heartbeat in nature. Let us rest here for a moment and consider something that most people never think about. The tide does not only lift the water, it lifts the land as well. The solid body of the Earth, this seemingly immovable rock beneath your feet, flexes and deforms under the gravitational pull of the moon and sun, just as the ocean does. This is called the Earth tide, or sometimes the body tide, and it is a real, measurable phenomenon. Twice each day, the ground beneath you rises and falls by roughly a foot, sometimes a little less, sometimes a little more, depending on the alignment of the moon and sun. You never feel it, because everything around you rises and falls together like passengers on an impossibly slow elevator. There is no jolt, no creak, no sense of motion at all. And yet sensitive instruments, gravimeters, tiltmeters, GPS receivers of extraordinary precision, have confirmed this motion beyond any doubt. The discovery that the solid Earth itself responds to tidal forces has been refined over more than a century of measurement, and it tells us something profound about our planet. The Earth is not perfectly rigid. It yields ever so slightly to the same forces that shape the sea. In a poetic sense, the planet breathes along with its ocean, and there is still more. Even the atmosphere experiences tidal forces, though atmospheric tides are complicated by other effects. Heating from the sun, pressure systems, wind patterns that can mask the gravitational signal. Scientists have identified a small but real lunar atmospheric tide, a rhythmic variation in air pressure that follows the moon's position, though it is far weaker than the dominant solar atmospheric tide, which is driven largely by thermal heating rather than gravity. So the entire Earth, its water, its rock, its air, responds to the gentle pull of distant worlds. Nothing is truly still. Everything flexes, everything yields, everything moves in slow, patient cycles that most of us will never notice. And perhaps that is the most soothing thought of all, that even the ground you rest upon is rocking ever so gently in time with the moon, as it has done for billions of years, and as it will continue to do long after we are gone. For most of human history, the tides were a mystery, powerful, reliable, and utterly unexplained. Ancient Greek observers noticed the connection between the tides and the moon. Pytheas of Massalia, a Greek explorer who lived in the 4th century BCE, is among the earliest known writers to describe the relationship between lunar phases and tidal strength, based on his voyages to the Atlantic coasts of Europe. The Roman naturalist Pliny the Elder, writing in the 1st century CE, also noted the correlation, recording that tides were strongest at the new and full moon. And yet, knowing that the moon was involved did not explain how or why. For centuries, various theories were proposed. Some imagined the Earth breathing, literally inhaling and exhaling seawater through subterranean caverns. Others suggested whirlpools or underground rivers. The great medieval Arab scholar Al-Kindi, writing in the 9th century, proposed that the moon's light, not its gravity, somehow heated the ocean and caused it to expand. It was an ingenious idea, but ultimately incorrect. The breakthrough came with Newton. In his Principia, he demonstrated that the same force that causes an apple to fall, gravity, also governs the motion of the moon around the Earth and the Earth around the Sun. And he showed, through mathematical reasoning, that the differential gravitational pull of the moon across the Earth's diameter was sufficient to raise the tides. This was revolutionary. For the first time, the tides were not mysterious, not supernatural, not the breath of a sleeping giant. They were the natural, calculable consequence of universal gravitation. Later, in the 18th and 19th centuries, mathematicians like Pierre-Simon Laplace refined Newton's tidal theory considerably, introducing what is now called the dynamic theory of tides, which accounts for the fact that the oceans are not uniform in depth, that continents interrupt the flow of water, and that the Earth's rotation introduces complex patterns of oscillation. The tides, it turns out, are not simply bulges that stay fixed beneath the moon. They are waves, enormous, slow waves that propagate through ocean basins, reflecting off coastlines, funneling through straits, and resonating in ways that depend intimately on the shape of the sea floor. And so the tides are both simpler and more complex than they first appear. A gravitational truth wrapped in the particular, beautiful geometry of our planet. Consider for a moment the Bay of Fundy, a long, narrow inlet on the eastern coast of Canada between the provinces of New Brunswick and Nova Scotia. Here, the tides are the most extreme on Earth. The difference between high tide and low tide in certain parts of the bay can exceed 50 feet, roughly the height of a 5-story building. Twice a day, approximately 100 billion tons of seawater flow in and out of this single bay, more water than the combined flow of all the world's freshwater rivers. And the reason is not that the moon pulls harder here than elsewhere. The gravitational force is essentially the same across the region. What makes the Bay of Fundy extraordinary is its shape. The bay is roughly 170 miles long, and it narrows and shallows as it extends inland. This geometry creates a natural resonance, much like the way blowing across the top of a bottle produces a tone. The time it takes for a tidal wave to travel from the mouth of the bay to its head and back again is very close to the roughly 12 hours and 25 minutes between successive high tides. This near match means that each incoming tide reinforces the previous one, amplifying the water's rise in a phenomenon known as tidal resonance. The effect is extraordinary. At low tide, the bay floor is exposed for vast distances, mud flats stretching to the horizon, strewn with boulders and sculpted sandstone formations called flowerpot rocks, carved over millennia by the relentless motion of the water. At high tide, those same formations are submerged beneath fathoms of cold, churning sea. The ecosystem that depends on this rhythm is remarkable as well. The Bay of Fundy is one of the most important feeding grounds for migratory shorebirds in the Western Hemisphere. Semi-palmated sandpipers gather there by the hundreds of thousands each summer, feasting on tiny mud shrimp that thrive in the tidal flats, building the fat reserves they need for their non-stop flight to South America. The tides set the table for them, exposing a banquet twice a day, then sweeping it clean and laying it again. It is a reminder that the moon's gravity does not merely move water, it shapes entire ecosystems, feeding millions of living creatures through a chain of cause and effect that begins 250,000 miles away in the silence of space. Now, let your mind drift deeper away from shorelines and mudflats into the open ocean itself, the deep, dark, immeasurable middle of the sea, where the surface stretches unbroken to every horizon. You might expect the tides to be most dramatic here, in the open water, far from the complications of coastlines. But in truth, the open ocean tide is surprisingly modest. In the deep sea, the tidal range, the difference between high and low water, is typically only about 1 to 3 feet. This seems almost impossibly small when you consider the enormous forces at work, but it makes sense when you remember the scale involved. The ocean is vast, and the tidal bulge is spread across thousands of miles. It is an incredibly gentle slope, a rise of a few feet over a horizontal distance that might span half an ocean basin. If you were floating in the middle of the Pacific during a tidal cycle, you would never notice the change. The water would rise and fall beneath you so slowly, so gradually, that it would be imperceptible without instruments. It is only when that broad, gentle wave encounters a coastline, when all that moving water is compressed into a narrowing space, funneled into bays and estuaries and river mouths, that the tide becomes dramatic. The shape of the seafloor matters enormously. Continental shelves, those submerged extensions of the continents that slope gently outward before plunging into the deep, act as ramps that amplify the incoming tidal wave. Narrow channels concentrate the flow, islands redirect it, underwater ridges split and scatter it into complex interference patterns. This is why tidal ranges vary so dramatically from place to place. In the Mediterranean Sea, which is nearly enclosed and connects to the Atlantic through the narrow Strait of Gibraltar, tides are often only a few inches. In certain parts of the English Channel, where the geometry of the sea floor and the coastline conspire to funnel the tidal wave, the range can exceed 30 feet. The same gravitational force acts everywhere, but the Earth's particular geography, its unique, unrepeatable arrangement of land and sea, transforms that single, simple force into an infinite variety of local expressions. Every coastline tells the same story differently. There is another dimension to the tides that deserves our attention tonight: time. Not the hours between one high tide and the next, but the vast stretches of geological time over which the tides have been slowly, imperceptibly reshaping the relationship between the Earth and the Moon. Here is the mechanism. As the Earth rotates, it carries its tidal bulges slightly ahead of the Moon's position because the Earth spins faster than the Moon orbits. The Moon completes one orbit roughly every 27.3 days, while the Earth rotates once every 24 hours. This means the tidal bulge on the near side of the Earth is not directly beneath the Moon. It is carried slightly forward, rotated ahead by the Earth's spin. That offset matters because the bulge has mass, and its gravitational pull tugs the Moon forward in its orbit, ever so slightly, giving it energy. As the Moon gains orbital energy, it moves to a higher orbit. It drifts farther from the Earth. This process is called tidal acceleration, and it has been precisely measured. Lunar laser ranging experiments, which bounce laser beams off retroreflectors placed on the Moon's surface by the Apollo astronauts and the Soviet Lunokhod rovers, have shown that the Moon is receding from the Earth at a rate of approximately 1.5 inches, about 3.8 centimeters, per year. That is roughly the rate at which your fingernails grow. It seems negligible, and over a human lifetime, it is. But over billions of years, the effect is enormous. When the Moon first formed, current evidence suggests this happened roughly 4.5 billion years ago, likely from debris ejected by a massive collision between the early Earth and a Mars-sized body sometimes called Theia. The Moon was much closer to the Earth than it is now, perhaps only about 15,000 miles away, compared to today's average distance of 239,000 miles. The tides in that ancient ocean would have been extraordinary. Towering walls of water, hundreds of feet high, crashing across a world that rotated far faster than it does today, completing a full day in perhaps only 6 hours. And there is the other half of this exchange. As the Moon gains energy and recedes, the Earth loses rotational energy and slows down. The tides are a break, and the days are getting longer. The slowing of the Earth's rotation is not a theory. It is a measured fact, confirmed by multiple independent lines of evidence. Atomic clocks, which measure time with extraordinary precision, have shown that the average day is growing longer by approximately 2.3 milliseconds per century. That number seems impossibly small, and over any span of time you or I might care about. It is. But over geological ages, it accumulates into something profound. We know this because the ancient Earth left records of its rotation in the most unexpected of places, in the growth patterns of corals and the layered sediments of tidal deposits. Fossil corals from the Devonian period, roughly 380 million years ago, show daily growth bands, fine ridges laid down each day as the coral grew, much like tree rings. By counting these bands within annual growth cycles, paleontologists have determined that a Devonian year contained approximately 400 days. Since the length of a year, the time for one orbit around the Sun has not changed significantly. This means that each Devonian day was shorter, roughly 22 hours long. The Earth was spinning faster then, and the Moon was closer. Going back further still, tidal rhythmites, layered sedimentary deposits that record the daily and monthly cycles of ancient tides, found in rocks dating to roughly 620 million years ago in South Australia, suggest that the day was approximately 21 hours long at that time. These are rocks that remember the rhythm of the Moon from more than 500 million years ago. It is a staggering thought that the quiet, invisible friction of the tides, acting grain by grain, wave by wave, over hundreds of millions of years, has measurably slowed the rotation of our entire planet. The days you experience now, each one 24 hours long, are a gift of this slowing, a tempo set by the patient, ceaseless pull of the Moon upon the sea, and the process continues. 1 billion years from now, if the Earth and Moon endure, the day will be considerably longer than it is today, and the Moon will hang farther away in the sky, appearing slightly smaller. The tides will be gentler then, softer as the distance between the two worlds grows, but they will never stop. Not while there is water, and not while there is a moon to call it. Let us turn now to a question that may have drifted through your mind as you listen. Do tides occur only on Earth? The answer is no, and the universe is rich with tidal phenomena far more dramatic than anything we experience here. Consider the moons of Jupiter. The giant planet, with a mass more than 300 times that of Earth, exerts tremendous gravitational influence on its many satellites. One of these, a moon called Io, is the most volcanically active body in the entire solar system. Io orbits Jupiter at an average distance of roughly 262,000 miles, and it is locked in an orbital resonance with two other large moons, Europa and Ganymede. This resonance keeps Io's orbit slightly elliptical, meaning its distance from Jupiter varies as it goes around. As Io moves closer and farther from Jupiter during each orbit, the tidal forces acting on it change, and the entire moon flexes. Its solid rocky body is squeezed and stretched rhythmically, like a ball of dough being kneaded by invisible hands. This relentless flexing generates enormous amounts of internal heat through friction, and that heat drives the hundreds of active volcanoes that dot Io's tortured surface, some of which send plumes of sulfur and sulfur dioxide hundreds of miles into space. Io's tides are not gentle. They are violent, world-shaping forces. And then there is Europa, another of Jupiter's large moons, slightly smaller than our own moon. Europa's surface is a shell of water ice, and beneath that shell, current evidence strongly suggests there exists a global ocean of liquid water. Kept liquid not by sunlight, which is feeble this far from the sun, but by tidal heating, the same flexing that torments Io, though in a gentler form. This subsurface ocean may contain more water than all the oceans of Earth combined. Scientists consider Europa one of the most promising places in the solar system to search for extraterrestrial life, precisely because it has liquid water, a source of energy in tidal heat, and the chemistry necessary for biology as we understand it. The tides of Jupiter may be nurturing life in an ocean that has never seen the sun. It is a thought worth holding gently as you drift closer to sleep. Back here on Earth, the tides shape life in ways both vast and intimate. Along every coastline where the tide reaches, there exists a narrow strip of world that belongs neither entirely to the sea nor entirely to the land. This is the intertidal zone, a place of extremes, of constant change, where organisms must endure being submerged in cold salt water for hours, then exposed to air, wind and sun, then submerged again. It is one of the most demanding habitats on the planet, and it's also one of the most biologically rich. The intertidal zone is typically divided into several bands. Nearest the low tide line, in the lower intertidal, you find creatures that spend most of their time underwater: sea stars, sea urchins, anemones, and forests of kelp and other algae. These organisms are exposed to the air only briefly during the lowest tides, and many cannot survive prolonged drying. Higher up, in the middle intertidal, mussels and barnacles cling to the rocks in dense colonies, filtering food from the water when submerged and clamping shut to retain moisture when exposed. Barnacles are extraordinary creatures. They are crustaceans, relatives of crabs and shrimp, that cement themselves permanently to rock surfaces and spend their lives feeding by extending feathery appendages to sweep plankton from the passing water. Near the high tide line in the upper intertidal and the splash zone, life becomes sparse. Only the hardiest organisms survive here: certain lichens, periwinkle snails, and tough, desiccation-resistant algae. These creatures may be wetted by the sea only during the highest spring tides or during storms, spending most of their existence in air. Every creature in the intertidal zone has evolved to match the tide's rhythm. Their feeding, their breeding, their very metabolism is tuned to the rise and fall of the water. Some species release their eggs only at specific tidal phases, synchronizing reproduction with the currents that will carry their larvae to new habitats. The grunion, a small fish found along the coast of California, rides the highest spring tides onto sandy beaches to lay its eggs at the very peak of the water's reach, ensuring that the eggs will be buried in sand and incubated in air until the next spring tide washes them free. Life, it seems, listens to the moon as carefully as the sea does. There is one more tidal phenomenon worth visiting tonight, something so dramatic and so beautiful that it has captivated observers for centuries: the tidal bore. In certain rivers around the world, the incoming tide does not simply raise the water level gradually. Instead, it arrives as a single, visible wave that travels upstream against the current of the river itself. This wave, the bore, can range from a gentle ripple to a churning wall of water several feet high, depending on the conditions. Tidal bores form when a large tidal range is funneled into a shallow, narrowing river or estuary. As the tide rises rapidly, the incoming seawater cannot spread out. It is compressed by the riverbanks and the shallowing bottom, and the leading edge of the tide steepens into a wave front that advances inland. The Qiantang River in eastern China produces one of the world's most spectacular tidal bores, a thundering wall of water that can reach heights of nearly 30 feet and travel upstream at speeds of up to 25 miles per hour. The Chinese have observed and celebrated this bore for over 2,000 years. Historical records from the Han Dynasty, more than 2 millennia ago, describe crowds gathering to watch the great wave arrive. In England, the River Severn produces a smaller but well-known bore, where the incoming tide from the Bristol Channel is funneled into the narrowing Severn estuary. The Severn bore is typically a few feet high, but during the largest spring tides, it can be large enough to surf. And people do, riding the wave upstream for miles through the quiet English countryside. The Amazon River also experiences a tidal bore, known locally as the pororoca, from a Tupi word meaning great roar. This bore can reach heights of around 13 feet and travels many miles inland, crashing through the jungle-lined banks of the lower Amazon, uprooting trees and churning the chocolate-brown river water into foam. And yet, for all their drama, tidal bores are still just tides. The same patient gravitational conversation between Earth and Moon, expressed through the unique geometry of a particular river at a particular moment. The Moon does not know it is making waves. The river does not know it is being visited. It simply happens, as it always has, the way gravity always does its work, silently, inevitably, and without any need for permission. As you settle deeper into rest, let us follow the tides into one of the most practical chapters of their long story, humanity's efforts to capture the energy of the rising and falling sea. The idea is ancient. Tide mills, which use the incoming tide to fill a reservoir and then release the water through a water wheel as it drains at low tide, have been used in Europe since at least the early Middle Ages. Archaeological evidence suggests that tide mills existed along the coasts of Ireland and Britain as far back as the 6th century CE. They were elegant in their simplicity. The tide filled the mill pond for free, and gravity emptied it through a mechanism that ground grain or powered machinery. In the modern era, engineers have pursued far more ambitious projects. The world's first large-scale tidal power station, the Rance Tidal Power Station, began operating in 1966 along the estuary of the Rance River in Brittany, France. It uses 24 turbines built into a barrage, essentially a dam, across the estuary, and it generates approximately 540 gigawatt hours of electricity per year, enough to supply a city of several 100,000 people. For decades, it was the largest tidal power station in the world, though it has since been surpassed by the Sihwa Lake Tidal Power Station in South Korea, which began operating in 2011 and has a capacity of approximately 254 megawatts. Newer approaches include tidal stream generators, which work somewhat like underwater wind turbines, placed in channels where the tide flows swiftly. These do not require a barrage across an entire estuary, which reduces their environmental impact. And yet, tidal energy remains a small fraction of the world's electricity supply. The challenges are significant. The infrastructure is expensive, suitable sites are geographically limited, and the environmental effects of barrages on estuarine ecosystems can be considerable. Still, tidal power has one great advantage over most other renewable sources. It is almost perfectly predictable. The tides follow the moon with mathematical precision. Unlike wind, which shifts and dies unpredictably, and unlike solar energy, which depends on cloud cover, the tides arrive on schedule, twice a day, every day. And they will continue to do so for as long as the moon orbits the Earth. There is something quietly reassuring about a power source that has never missed an appointment in 4.5 billion years. There is a final thought I would like to leave with you before we ease towards silence. A thought about the far future, the very long future of the tidal relationship between Earth and Moon. We spoke earlier of how the Moon is slowly receding and the Earth's rotation is slowly decreasing. If we project these trends forward, understanding that such projections involve considerable uncertainty over billions of years, scientists believe that the Earth and Moon are moving toward a state called tidal locking. In tidal locking, the rotation of one body slows until it matches the orbital period of the other, so that the same face is always presented. This has already happened to the Moon. It is tidally locked to Earth, which is why we always see the same side. The Moon rotates exactly once for every orbit it completes, a consequence of the Earth's tidal forces acting on the Moon over billions of years, gradually slowing the Moon's rotation until it's synchronized with its orbital period. In the very distant future, estimates vary, but some calculations suggest tens of billions of years from now, the Earth may become tidally locked to the Moon as well. If that were to happen, the Earth's day and the Moon's orbital period would be the same length, roughly 47 of our current days. The Moon would hang motionless in one part of the sky, visible only from one hemisphere of the Earth, forever. Tides, as we know them, would essentially cease because the tidal bulge would no longer sweep around the planet. The ocean would settle into a permanent, fixed distortion, slightly elongated toward and away from the Moon, but no longer rising and falling. Of course, this particular future may never fully arrive, because the Sun will exhaust its hydrogen fuel and expand into a red giant in approximately 5 billion years, likely engulfing or profoundly disrupting the inner solar system long before tidal locking completes. The ultimate fate of the Earth-Moon system depends on stellar evolution, not just tidal mechanics, but the direction of the journey is clear. The tides are slowly winding down, spending the Earth's rotational energy, exchanging it for distance between the worlds. What we experience tonight, this gentle rise and fall, is a momentary snapshot of a process that began when the Moon was born and will not end until the physics of the situation reaches equilibrium, or until the Sun decides otherwise. And so we arrive at the last gentle thought of our journey, the tides as a kind of music, a vibration woven through the fabric of our world. If you could listen to the tides the way you listen to a piece of music, you would hear layers upon layers of rhythm. The twice-daily rise and fall of the semi-diurnal tide, the fortnightly waxing and waning between spring and neap, the monthly variation as the Moon swings closer and farther from the Earth in its slightly elliptical orbit, the semi-annual peaks when the Sun crosses the equator at the equinoxes, and even longer cycles tied to the slow precession of the Moon's orbital plane, which completes a full rotation roughly every 18.6 years. This last cycle, known as the lunar nodal cycle, subtly modulates tidal ranges over nearly 2 decades, and it is one of the factors that tidal scientists must account for when making long-term predictions. All these rhythms overlap and interfere, creating a complex but entirely predictable pattern, a kind of gravitational chord played continuously across the surface of the planet. And it is worth noting that this music is not merely poetic metaphor. Oceanographers decompose the tides mathematically into what are called harmonic constituents, individual sinusoidal waves, each with its own frequency, amplitude and phase corresponding to a specific astronomical influence. The dominant constituent, called M2, represents the principal lunar semi-diurnal tide and has a period of 12 hours and 25.2 minutes. There are dozens of other constituents: S2 for the principal solar semi-diurnal tide, N2 for the lunar elliptic variation, K1 and O1 for diurnal components. each one a note in the gravitational score. By measuring the tides at a given location for a sufficiently long time, scientists can identify all the significant constituents and then predict the tides at that location far into the future with remarkable accuracy. This is why tide tables can be published years in advance and remain trustworthy to within a few minutes. The ocean is not chaotic in this regard. It is obedient. It follows the music of gravity with extraordinary fidelity, and it has done so since the first water gathered on this planet and the first moon rose above the horizon. Tonight, that same music is playing still, just outside the reach of your hearing, the ocean breathing in its sleep as you breathe in yours. Consider for a moment how the tides have shaped the very edges of continents, not in a single dramatic gesture, but through a patience so profound it spans geological time. Every coastline you have ever seen, every gentle cove and weathered cliff, every sandy beach curving softly toward the horizon, has been sculpted in part by the ceaseless conversation between water and stone. The process is called tidal erosion, and it works on timescales that dwarf a human lifetime, wearing away rock grain by grain, tide by tide, century by century. Along the coasts of Normandy in France, the chalk cliffs stand white and luminous against the sea, and yet they are slowly retreating, losing on average roughly a few centimeters each year as the tides press and recede, dissolving the softer minerals and carrying them out into the deep. In other places, tides do the opposite. They build. Tidal flats, those vast expanses of mud and sand exposed at low water, accumulate sediment delivered by each incoming tide, layering it gently like pages in a book that no one will ever finish writing. Over thousands of years, these flats can grow into marshlands, rich with grasses and burrowing creatures, entire ecosystems born from the simple act of water setting down what it carries. And there is something deeply comforting in this, the knowledge that the same force that rocks you toward sleep tonight is also somewhere far away, quietly reshaping the earth. The tides do not hurry. They do not force. They simply arrive, do their ancient work, and withdraw, trusting that time will complete what a single tide cannot. If you were to stand on a rocky shore and press your hand against the stone, you would feel something solid, immovable, permanent. And yet the tides know otherwise. They know that even granite yields to water, given enough patience, enough repetition, enough gentle insistence. It is a lesson the ocean teaches without words, that persistence, applied softly and without urgency, can reshape anything. Let that thought settle into you now, as quiet and certain as the tide itself. There is another gift the tides offer to the living world, one that unfolds in the liminal space between land and sea, in that narrow ribbon of shore that is sometimes submerged and sometimes exposed. Biologists call this the intertidal zone, and it is among the most dynamic habitats on Earth. A place where life must be extraordinarily adaptable, able to endure both the crushing pressure of waves and the drying heat of open air within the span of a single day. Tide pools form in the hollows of rocky shores when the water recedes, and within these small temporary worlds, entire communities persist. Sea anemones with their soft, petal-like tentacles swaying in still water, hermit crabs navigating miniature landscapes of barnacle-covered stone, and tiny sculpins hovering motionless in the shallows, waiting for the ocean to return. These creatures have evolved over millions of years to thrive in a world defined by rhythm, by the reliable coming and going of the sea. Some mussels, for example, open their shells to feed only when the tide covers them, filtering plankton from the cold salt water, then clamping shut when the air returns, sealing moisture inside to survive the hours of exposure. Certain species of algae time their reproduction to the tidal cycle, releasing spores only during specific phases of the tide so that the water will carry them to favorable ground. Current evidence suggests that many intertidal organisms possess internal biological clocks tuned not only to the roughly 24-hour cycle of day and night, but also to the approximately 12-hour and 25-minute cycle of the tides themselves. Even when removed from the ocean and placed in a laboratory, some of these creatures continue to follow tidal rhythms for days or weeks, opening and closing as though the sea were still breathing around them. It is as if the tide has written itself into their biology, become a part of their cellular memory. And perhaps, in your own quiet way, you too carry something of the ocean's rhythm within you, a deep ancestral knowing that it is safe to rest when the world grows still, that the water will return, that morning will come. Let us drift now to a thought that is almost impossibly vast and yet strangely soothing. The idea that tides are not unique to Earth. Wherever gravity reaches across space, wherever one body orbits another, tidal forces are at work, stretching and compressing matter with a patience that spans billions of years. Jupiter's moon Europa, a world roughly the size of our own moon, is encased in a shell of ice that may be 10 to 30 kilometers thick, and beneath that frozen surface, scientists believe there exists a liquid ocean, kept warm not by sunlight, which barely reaches that far-flung corner of the solar system, but by tidal heating. As Europa orbits Jupiter, the immense gravity of the giant planet flexes the moon's interior, squeezing and releasing it in a rhythmic pulse, and this mechanical flexing generates friction, which generates heat, enough heat to keep water liquid in a place where temperatures on the surface plunge to roughly minus 160 degrees Celsius. It is one of the most extraordinary ideas in modern planetary science that the same gravitational dance that moves our oceans might sustain a hidden sea beneath the ice of another world, a sea that some researchers consider one of the most promising places in our solar system to search for extraterrestrial life. Saturn's moon Enceladus tells a similar story. Observations from NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, revealed plumes of water vapor and ice particles erupting from cracks near the moon's south pole, strong evidence of a subsurface ocean kept liquid by tidal forces. And so the tides, which began in our story as the gentle rise and fall of water on a familiar shore, reveal themselves to be a universal phenomenon, a consequence of gravity itself, operating on scales from the smallest tide pool to the moons of distant gas giants. Somewhere out there, in the cold silence between stars, tidal forces may be warming oceans we have not yet discovered, sustaining possibilities we have not yet imagined. Let that vastness cradle you, not with its enormity, but with its quiet promise that the universe is endlessly, gently alive. And now, as we draw these threads together, let your thoughts rest on one last beautiful detail, the sound of the tides. If you have ever fallen asleep near the ocean, you know that the rhythm of the waves carries a quality that no other sound on Earth quite replicates. There is the slow gathering of water as it approaches the shore, a deepening hush that seems to draw everything toward it, and then the soft exhalation of the wave as it breaks and spreads across the sand, followed by the gentle hiss of water retreating over countless tiny grains, each one rounding the sound into something smooth and continuous. Researchers who study acoustics have found that ocean waves produce a broad spectrum of frequencies, a kind of natural white noise that masks the sharper, more irregular sounds that tend to keep the brain alert. Some studies suggest that this consistency of sound helps the auditory cortex relax its vigilance, allowing the brain to ease more readily into the slower wave patterns associated with deep sleep. It is possible, some scientists propose, that our responsiveness to the sound of the sea has roots in our evolutionary past, when the rhythmic pulse of water along a shoreline may have signaled safety, a stable environment, a reliable source of food, an absence of sudden danger. Whether or not that hypothesis proves true, the experience itself is undeniable. The ocean's voice soothes us in ways that feel older than language, older than memory. And so, even now, far from any coast, you can carry the idea of that sound within you. Imagine it gently, the long, patient approach of the wave, the soft tumble of foam over wet sand, the quiet retreat of water pulling back toward the deep. Each cycle takes roughly 8 to 12 seconds on a calm night, a tempo so close to the rhythm of restful breathing that the two seem to merge. The ocean breathing with you, or perhaps you breathing with the ocean. Let each imagined wave carry you a little further from wakefulness, a little deeper into the warm, dark stillness where sleep waits for you, as patient and as certain as the tide, as certain. Consider for a moment the tides of worlds other than our own, for wherever gravity reaches across space and finds a willing body of fluid, tides will follow, patient and inevitable. Jupiter's moon Europa, buried beneath a shell of ice perhaps 10 to 30 kilometers thick, is believed to harbor a global ocean of liquid water kept from freezing not by the warmth of a nearby star, but by the relentless kneading of tidal forces. Jupiter is so massive, roughly 318 times the mass of Earth, that its gravitational grip on Europa flexes the little moon's interior with every orbit. This tidal heating, as scientists call it, generates enough energy to maintain liquid water beneath that frozen crust, creating conditions that some researchers consider among the most promising in our solar system for the possibility of life beyond Earth. And Europa is not alone in this. Enceladus, a small moon of Saturn, barely 500 kilometers across, shoots plumes of water vapor and ice particles into space from fractures near its south pole, geysers powered by tidal forces that squeeze and stretch its icy body as it orbits the ringed giant. The Cassini spacecraft, which studied Saturn and its moons from 2004 to 2017, flew through those plumes and detected not only water but also organic molecules and molecular hydrogen, hints that hydrothermal activity may be occurring on the ocean floor of that tiny world. Even Io, another of Jupiter's large moons, experiences tides so extreme that they do not merely warm an ocean but melt rock itself, making Io the most volcanically active body known in the solar system, with hundreds of active volcanoes reshaping its sulfurous surface. So the same fundamental force that draws the waters of our own oceans gently upward twice each day is also elsewhere in the cosmos, cracking ice, heating stone, and perhaps in ways we do not yet understand, nurturing the fragile chemistry from which life might one day emerge. The tides are not merely an earthly phenomenon. They are a universal conversation between mass and motion, spoken wherever gravity finds something soft enough to answer. Let us return now to the shores of our own world, where the tides have shaped not only the land and the living things upon it, but also the long story of human civilization. For thousands of years, people who lived near the coast learned to read the tides as one reads the face of a trusted companion, noticing every subtle shift, every pattern, every promise. Ancient coastal communities around the world built fish traps that worked in concert with the falling tide, stone walls and woven barriers, arranged so that fish swimming freely at high water would find themselves stranded in shallow pools as the sea retreated. Examples of these tidal fish traps have been found in places as distant from one another as the coast of Wales, the shores of Australia, and the bays of British Columbia, each culture independently discovering the same quiet principle, that the tide's retreat is a gift if you know how to receive it. In the Bay of Fundy, between the Canadian provinces of New Brunswick and Nova Scotia, the tides reach heights that are among the most extreme on Earth, with a tidal range that can exceed 16 meters, roughly the height of a 5-story building. This remarkable range arises in part because the bay's shape and depth create a resonance effect, where the natural period of water sloshing back and forth in the basin closely matches the roughly 12.5-hour cycle of the tides, amplifying the rise and fall far beyond what the open ocean alone would produce. The Mi'kmaq people, who have inhabited those shores for thousands of years, developed a deep understanding of these waters long before European contact, their knowledge woven into oral traditions that respected the rhythm of the bay. And in medieval Europe, monks and scholars began compiling tide tables, attempting to predict the ocean's movements so that ships could safely enter and leave harbors. The Venerable Bede, writing in the early 8th century in his work De Temporum Ratione, was among the first in Europe to describe the relationship between the moon and the tides with careful attention, noting that the timing of high water varied from port to port. There is a kind of music in the mathematics of the tides, a quiet harmony that reveals itself only to those who listen with patience and care. In the 19th century, the great British physicist Lord Kelvin, born William Thomson in 1824, devised one of the most elegant machines ever built to predict the rise and fall of the sea. It was called a tide predicting machine, and it worked by adding together a series of simple wave-like motions, each representing one of the gravitational influences that contribute to the tides. The moon's pull was one component, the sun's another, and then there were corrections for the elliptical shape of the moon's orbit, the tilt of Earth's axis, the varying distance between Earth and Sun across the seasons, and dozens of other subtle factors. Each of these influences could be described as a single smooth wave with its own period and amplitude, and when all of them were layered together, the resulting curve matched the actual behavior of the tides at a given port with remarkable fidelity. Kelvin's machine used a system of pulleys, cranks, and wires to physically sum these waves, tracing the predicted tide height on a roll of paper as a pen moved up and down. Later versions of the machine incorporated as many as 40 or more individual components, each turning at its own rate, and the device could crank through an entire year of tide predictions in just a few hours. This approach, known as harmonic analysis, remains the foundation of tidal prediction to this day, though the gears and pulleys have long since given way to digital computation. What is beautiful about this method is the underlying idea that something as complex and seemingly capricious as the ocean's breathing can be understood as the sum of many simple, overlapping rhythms, each one tracing a circle in the sky or a wobble in the geometry of celestial orbits. And so, the tide is not chaos. It is a chord made of many notes, each one played by gravity on the strings of water and time. And if you learn to hear the individual notes, you can predict where the ocean will be tomorrow, next month, or a century from now. And yet, for all our ability to predict the tides with exquisite precision, there remain aspects of this phenomenon that still carry a sense of quiet mystery. One of the most intriguing is the question of how the tides dissipate their energy. As the tidal bulge sweeps across the planet, it does not move frictionlessly. The water drags against the ocean floor, particularly over shallow continental shelves and through narrow straits, and this friction converts the kinetic energy of the moving water into heat. The amount of energy involved is staggering. Current estimates suggest that the tides dissipate roughly 3.5 terawatts of power, which is comparable to the total electrical power consumption of all human civilization. Most of that energy, approximately 2/3, is lost to friction between the tidal currents and the shallow seafloor, while the remaining third is believed to be dissipated in the deep ocean, where internal tides, great slow waves moving through the layered interior of the sea, break against underwater ridges and seamounts. These internal tides are invisible at the surface, hidden movements of water that can travel thousands of kilometers before surrendering their energy to turbulence and mixing. And that mixing matters profoundly because it stirs the deep ocean, bringing cold, nutrient-rich water upward and cycling heat downward, a process that helps regulate Earth's climate over timescales of centuries and millennia. Without tidal mixing, scientists believe the deep ocean would become more stratified, more stagnant, and the distribution of heat and nutrients across the planet would shift in ways that could alter weather patterns and marine ecosystems dramatically. So as you lie here now, breathing softly, the tides are working in the darkness beneath the waves, stirring the deep waters of the world, carrying warmth and nourishment through the hidden interior of the sea. It is a labor that never ceases, powered by the slow orbital dance of the moon, a dance that has been gradually widening for billions of years as the tides steal angular momentum from Earth's rotation and offer it to the moon's orbit. Everything is connected. The slowing of our days, the retreating moon, the stirring of the deep. Consider, for a moment, the creatures who have entrusted their entire existence to the rhythm of the tides, those ancient and patient beings whose lives are written in the language of ebb and flow. Along rocky coastlines around the world, there exist narrow bands of life called intertidal zones, places that are neither fully ocean nor fully land, but something older and stranger than either. Here, twice each day, the sea arrives like a gentle visitor, filling pools and covering stones, bringing oxygen and nutrients and the small drifting organisms that feed an entire hidden world. And twice each day, the sea withdraws, leaving behind a landscape that must endure exposure to sun and wind and the sharp attention of shorebirds. The creatures that thrive in this liminal space have evolved over hundreds of millions of years to read the tidal clock with extraordinary precision. Mussels open their shells to feed when the water covers them and clamp shut as the tide retreats. And remarkably, scientists have observed that mussels transported to laboratories far from the coast will continue to open and close on a tidal schedule for weeks, as though the memory of the moon's pull lives somewhere deep within their tissues. Fiddler crabs darken their shells during low tide to protect against ultraviolet radiation and lighten them again when the water returns, a color change tied not to what they see, but to an internal calendar synchronized with lunar cycles. Certain species of grunion, small silvery fish found along the coast of California, ride the highest tides of the month onto sandy beaches to lay their eggs at the precise moment when the water reaches its furthest extent, ensuring that the eggs will remain safely buried in warm sand until the next set of high spring tides arrives, roughly 2 weeks later, to wash the hatched larvae into the sea. Even the humble limpet, that small conical snail clinging to wave-battered rocks, navigates home to the exact same resting spot after each foraging expedition, following a chemical trail it laid down during the previous tidal cycle. These are not conscious decisions in the way we understand choice, but rather the accumulated wisdom of evolution, a deep biological conversation between life and the gravitational forces that move the sea. And so the tides reach beyond our own planet, whispering their influence across the solar system in ways that remind us how deeply gravity connects all things. Jupiter's moon, Io, a world scarcely larger than our own moon, is the most volcanically active body known to science, and the reason lies entirely in tides. Jupiter's immense gravitational field, assisted by the orbital resonance of neighboring moons Europa and Ganymede, flexes and squeezes Io's interior with such relentless force that the rocky body generates enormous quantities of heat through a process called tidal heating. The surface of Io erupts with plumes of sulfur dioxide reaching hundreds of kilometers into space, painting the little moon in shades of yellow and orange and white, all because gravity will not let it rest. Farther out, beneath the icy crust of Europa, scientists believe that this same tidal flexing maintains a vast ocean of liquid water, an ocean that may contain more water than all of Earth's seas combined. The tides raised within Europa by Jupiter's gravity are thought to keep that hidden ocean from freezing solid, and where there is liquid water and a source of energy, there exists, at least in principle, the possibility of life. Saturn's moon Enceladus tells a similar story, its southern pole venting great geysers of water vapor and ice particles into space, material that feeds one of Saturn's faint outer rings. The Cassini spacecraft, which orbited Saturn from 2004 through 2017, flew through those plumes and detected complex organic molecules, silica nanoparticles suggesting hydrothermal activity on the ocean floor, and molecular hydrogen, a potential food source for microbial life. All of this driven by tides, by the patient and ceaseless kneading of gravity upon a small, icy world. Even Pluto and its large moon Charon likely experienced significant tidal heating in their early history, and some researchers propose that Pluto may still harbor a subsurface ocean kept liquid in part by the residual warmth of that ancient tidal interaction. The tides, it seems, are not merely a feature of our earthly shores, but a fundamental sculptor of worlds, quietly shaping the conditions for warmth and water, and perhaps even life itself across the darkness of space. And now the tide of your waking mind begins to ebb, gently, naturally, as all tides do. You have traveled far tonight, from the mathematics of gravity to the coral reefs of the ancient Devonian, from the volcanoes of Io to the mudflats of the Bay of Fundy, from the tidal bores of the Kiantang River to the quiet, inevitable future where the Earth and Moon drift slowly apart. Let all of it dissolve now, the way foam dissolves on a retreating shore. You do not need to hold any of it. The knowledge is there, settled, absorbed, like water sinking into sand. The tide will return, it always does. But for now, there is only stillness and the slow, ancient rhythm of gravity rocking the world to sleep, as it has done for 4.5 billion years. Let it rock you too. Let everything go. Sleep now. If the tides brought you peace tonight, you are always welcome here. A gentle tap on the subscribe button means we will be waiting for you tomorrow night with another quiet journey through the wonders of the world. Thank you for spending your night with Let's Learn while you sleep. Subscribe and come back tomorrow night. We'll be here. Sleep well.